So now that we have this notion of, molecules, and elements, we need to now discuss the notion of moles. And so when we look at moles, basically, since atoms are so small, we are basically forced to work with, very large amounts of atoms. It was found by, Avogadro that if you had 1 gram of hydrogen looking like this, right? Hydrogen with that atomic mass of 1 as well. You would have basically 6.022 times 10 to the 23rd atoms of hydrogen, or 1 mole of hydrogen atoms. So that's the big thing with from Avogadro, is that 1 gram of hydrogen, you now have a correlation between that and a mole of something, in this case atoms. And that's what we have to think about, this notion of the mole. Is the mole is really, for us chemists, I was going to say bakers there. It's really the chemist's dozen, right? If you look at a dozen, you would say 12, right? 12 eggs, that's a dozen eggs, right? Or, if you have the, with cookies, it would actually be 13, as far as a baker's dozen is actually 13. So we have this idea that describes the number, right? The dozen describes a number. Right, such as 12 equaling a dozen. Well, the chemist's dozen is not 12. Right, the chemist's dozen is basically a mole. And that is equal to 6.022 times 10 to the 23rd things. So just like you could have a dozen eggs, or a dozen cars, or a dozen blueberries, or a dozen apples, you could have a mole of apples, a mole of blueberries, right? A mole of eggs, right? It's really describing an actual number. And this is really a conversion for us, essentially. Right? It's basically saying that if I have carbon, carbon has a mass of 12 AMUs. But now, this is saying that 1 mole of carbon is equal to 12 grams of carbon, which is 6.022 times 10 to the 23rd atoms of carbon. So it's making a relationship between the idea of the mass of carbon that we see as far as the atomic mass to now this idea of mole. So it's taking it to the next level, that really 12 AMUs is more like saying, well, I have 12 grams of carbon per mole of carbon. And there is our conversion, right? Allowing us to go back and forth between the two. And this is our idea of atomic molar mass. Atomic molar mass is equal to grams of the element per mole of the element. So that's our relationship between, Avogadro's number, and now going into a different type of conversion unit for us, now grams per mole. And this is a hugely, extremely conversion component for us. We're going to be going a lot between the idea of mass and the idea of moles. That leads us to chemical formulas. And basically, chemical formulas now represent the ratio of one element to another within a molecule. Maybe you've heard the term molecular formula. So it's the same thing. Same thing. These ratios are whole numbers, or are simple whole numbers. We might be familiar with this particular molecule. This is glucose, or sugar. And so from this we could say, that one molecule of sugar has basically 6 carbons, 12 hydrogens, and 6 oxygens. That's all within that one molecule. But we can go one step further and say with that same molecule, we could now say that, well, 1 mole of sugar has basically 6 moles of carbon. 12 moles of hydrogen, and 6 moles of oxygen within the structure. So that's that inherent important relationship between now the formula, atoms, and moles, is that they're all really related to one another. They're all really saying the same thing as far as now allowing us to relate one thing to an actual another. Within formulas, there is what's known as the actual or true formula, which is the actual number of elements and their ratio to one another. Within a molecule. And then there's also this idea of empirical formula, which is the simplest number of elements in their ratio. So we have the simplest representation, which is the empirical formula. We have then, the actual representation, which is the actual or true formula. And as examples of that, we could have, C6 going back to our sugar example, right? This is our, actual, or true formula, but then we could also represent that as C3H6O3 or go even further, right, and say, oh, really it's C1H2O1. And that now is the simplest, or the empirical formula. So that's the nature of those two. We'll get more into that as we go. Let's look at another example here of, using molecular formula as a conversion. So in an example here, we could say how many moles of sodium citrate. Sodium citrate has this formula: 3 sodiums, 6 carbons, 7 hydrogens, and 8 oxygens are required to obtain 3.20 times 10 to the 22nd atoms of sodium. So this is, a conversion process that we have here. So I often tend to look at where I'm going to go, meaning where do I want to end up? And I'm looking for this particular molecule, and specifically moles of this particular molecule. So I got to get to that point from somewhere. And the starting point must be the other value that's being given to me here, the 3.20 times 10 to 22nd atoms of sodium. And so somehow I got to find the connection that goes between those two. And so what we would find is there's, hopefully two connections for us. I mean, first, what I see is, starting with atoms, and I need to get to moles. And so I immediately think of, Avogadro's number, right? That there's 6.022 times 10 to the 23rd atoms in 1 mole. So I can put that, within this context, right? That I have Avogadro's number helping me do some type of conversion to get to the mole value. And then I can use the molecule's formula to relate molecule to element. So we would be going somewhere in here, well, where we're now using the molecular formula to help with that process. So we could have, step 1 using Avogadro's number, step 2 using this formula, and then we are at our answer as far as moles of sodium citrate. So let's start with that measurement. Which we have here are atoms of sodium. And, we're starting with that notion of the measurement. And then we're going to apply conversions. So the first conversion would be looking at step 1, where we have 6.022 times 10 to the 23rd sodium atoms for every 1 mole of sodium atoms. And so that's allowing me to convert out of atoms of sodium and get into moles of sodium. And now I can go to the next conversion, where step 2, where now I'm actually using the molecule and its actual formula. That for every 1 mole of that sodium citrate, Na3C6H7O8, there's actually 3 moles of sodium. And I'm just getting that from the formula, right? In the formula, there's 3 sodiums beside this, 3 subscript beside the sodium. So that's where my number of sodiums is coming from. And so now it's my sodium atoms that's now being converted into the molecule that that sodium atom is actually a part of. And we end up with a value of 1.8 times 10 to the negative second moles of that sodium citrate. Right, would contain 3.022 times 10 to the 22nd sodium atoms. And so that's our first type of example of getting into Now using the molecular formula and relating it to elements within that formula and vice versa.